Good morning. Today's topic is isomorphism under the section of Introduction to Graph Theory. So let us see the definition of isomorphism. So isomorphism is nothing but you have to consider two graphs. You will be given two graphs. One is G and other one is G dash graph, which again has a corresponding vertices and edges. Again, this graph also has a vertices and edges. So you will tell that these two graphs are isomorphism. That means you will be given with the two graphs. One is the G with vertices and edges and G dash with the vertices and edges. You will tell that these two graphs are isomorphic in case if there is an one-to-one correspondence between the vertices of both the graphs and one-to-one correspondence of the edges between both the graph. So the definition will be consider two graphs, that is G and G dash. Suppose there exists a function f b to b such that f is in one-to-one correspondence for all vertices of a comma b of G and ab is an edge of G. That means for all vertices whatever is present in this particular graph, there should be a corresponding class. For example, if one graph has a b c d and in the second graph G dash has PQRS, then there should be only one-to-one corresponding between the vertices. It may be any correspondence, but there should be only one-to-one correspondence. So this is regarding the vertices. And also in case of edges, if you have AB as an edge, there should be a corresponding edge for AB in the another graph, that is G dash. So this would be nothing but the one-to-one correspondence between the vertices of graph, and also an AB is an edge of G if and only if function of a comma b, that means when you apply a function you'll get G dash, right? A comma b is an edge of G dash, then f is called an isomorphism between G and G dash, and we say that G and G dash are the isomorphic graph. So this is regarding the definition of the isomorphic. In other words, you can also tell that two graph G and G dash are said to be isomorphic if there is an one-to-one corresponding between their vertices and between their edges such that adjacency of vertices is preserved, then it is called an isomorphism. So this is regarding the definition of the isomorphism. Let us see an general example like how it works with the graph. So for example, let us consider this graph, that is AB, A, B, C and D, and then you have the edges as over here. Okay, and then also P, Q, R, S, PQRS. Okay, so these are the two graphs. When a vertex, now how will we tell that these two graphs are vertex? First, there should be an one-to-one correspondence between the vertices. So see that one-to-one correspondence means for each vertex of this graph there should be one each vertex over here also. So if you see the one-to-one correspondence between these two graphs, there should not be any extra graph in this. So you just check for the one-to-one correspondence. So if you take A, for that, for this vertex, which vertex is corresponding, you just check for the edges also, whether the edges also is having one-to-one corresponding. So A has three edges, so you choose anything which has three edges over here. So P has three edges, so A is in corresponding with P, so you can write one-to-one corresponding between the vertices as one-to-one correspondence between the vertices of these two graphs is A to P. That means for A you have a corresponding vertices P. Check for B. B also has three edges. Your Q you check, it has 1, 2 as well as 3 edges. Okay, so for this B we can write B over here. We can write C here, because why C? Because even C has three edges, and we can write D. So A over here. This is just for a simplification I wrote over here, A, B, C, D. So you can write the corresponding edge of vertices of B is Q and C is R and D is S. Okay, so you check with the one-to-one correspondent between the vertices, it's working, because for A you have 3 edges and correspondent you had put P 3 edges. For B you have 3 edges and here also Q you have 3 edges. For C you have 3 edges and R also has 3 edges. For S you have 3 edges and D also has 3 edges. This is a simple graph actually, where you will not have any complication, but there are some terms where exactly you need to check what is A in this second graph, how exactly. So depict whatever your A is there, going to identify that A in this particular graph would be difficult in the other example. So this is a simple example where all the vertices are having 3 edges. Here also all the vertices are having 3 edges. So you can correspond A to anything, not only P, you can correspond A to Q, A to R, A to S and A to P. Anyhow, all these four vertices also you can correspond. Any one of these 4 vertices you can correspond with A. But simply to simplify, I took A correspondence to P itself. So you have one-to-one corresponding between the vertices of these 2 graphs. So that is achieved. Next, you need to find the edges correspondence. Under this, the edges in the 2 graphs correspond with each other. Which are the edges that correspond with each other? So check for AB. AB means it is, here you write as it this simplification. So AB corresponds to what? So write this one-to-one correspondence. One-to-one correspondence between the edges are of edges of the two of these 2 graphs. Between the edges of these 2 graphs are, your A to B edge is there. For this corresponding, what is the edge between this? So we know that for A mapping vertex is P, for B mapping vertex is Q. So that edge itself you need to mention. So A to B, A comma B, then again this correspondence. Okay, and then here we have PQ. Similarly, AB is done. Next AC. AC means you have correspondent edge you have as P comma R. You can see I've written for that it's a simplification here. And AD means you have correspondent edges P comma S. P comma S. So you have AB, PQ, is AC as PR, and AD as PS, and left out is BC, and BC we did not write it, so we'll write BC over here. BC. For BC correspondent it is QR, and for BD, BC is there, then we need to find for this BD correspondent edge is QX, QS, and then you have CD. We did not do with the CD. For CD you have RS. So totally how many edges are there? So many edges you are going to list. That is 1, 2, 3, 4, 5 and 6. So for these 6 edges you are going to find the correspondence. If they are correspondent to each other, that means what? One edge has one correspondent edge over here, similar to that, one correspondent edge over here. And again all these edges will have a correspondent edge over here. Then these two both graphs are isomorphic. First job is you have to find the correspondent between the vertices, next you're going to find the corresponding between the edges. If you find both these two things are present in a particular graph, then both the graphs are said to be isomorphic. So this is regarding the definition of the isomorphic as well as the example problem, just an example of simple graph, how you're going to find the whether those two graphs are isomorphic or not. So let us solve the example problem in the next slide. So example 1 is you need to prove that these two graphs shown below are isomorphic. So before we check whether they are isomorphic or not, we need to check whether there are corresponding vertices as well as the corresponding edges. So just check for number of vertices. So you have totally 1, 2, 3, 4 vertices. Check over here also you have V1, V2, V3, V4, totally 4 vertices. So there are equal number of vertices. Check for the edges. You have 1, 2, 3, 4, 1, 1, 2 and 3 and 4. So there are 4 vertices as well as the 4 edges. So what you're supposed to do is, the initial step we are going to do is find the one, we are going to find the one-to-one correspondent between the vertices. One-to-one correspondence between the one-to-one corresponding between the vertices. So just check for the V1 vertex which we can do the corresponding vertex. So it has two edges. All these are having two edges. I mean two edges from them. So check here, V1, V2 has two edges, V3 has edges, V4. So we can directly put V1 within the bracket here. I'll put it as U1 and V2 I'll put it as U2. This just for your reference you can put it because you will not get any confusion. That means here they mentioned V1, V2, V3 itself, or else you can just put, yeah, better you, they have given both the graphs as V3, V4, or else you can just put, sorry, whatever is there in this particular graph itself you put over here. So if you put it as V1, here V2, here V3, V4 itself, and here V3 itself. So what is that? This is what is the second graph they have given to you, that is V1, V2, V3, V4. So here V1, V2, V3, V4. So we are going to find whether there is a correspondent correspondent edges and vertices are equal. So from V1 it has gone to V2 and V3. Okay, sorry, V1 it has gone to V2 and V3. So I cannot write this as V2 because there is no connection from V1 to V2. So what I need to do is, just a minute, so just check, I did this as V1, this as V1. So from V1 it has gone to V2 and V3. So V3 I can keep this itself, V3 I can keep this itself because one edge is gone, whereas V4 I need to do it as V2. Why? From V1, V2 it is gone. So left out is one vertex, so that would be obviously V1, V2, V3, V4. Okay, so we got to know what is the how we are going to find the vertices. So check from V1 it has gone to V2, V3. Similarly from here also, if you take this as V1, the two edges should go to V2 and V3. So which you are going to choose, V2 and V3 is left to you. So I choose this as V3 and other one as V2. Again from V3 it has to go to V4 and V1. V1 it is going, so this would be V4. Again from V4 it has to go to V2 and V3. So V2 is gone, V3 is gone. Again from V2 it has to go to V1 as well as V4. So everything is working fine. So I just found one-to-one correspondent between the vertices. So you should list what are the one-to-one correspondent between the vertices. So that is nothing but V1 to V1, V1 to V1. V2 of this is what actually? V2 of this, whatever I have written within the bracket is the vertices of the first graph. So that you're supposed to write the first. So I wrote V2, for that corresponding vertices V4, V4, and then V3 corresponding vertices V3 itself, then V4 corresponding vertices V2. I hope it's clear with how to find the one-to-one corresponding between the vertices. I'll repeat. First job we are going to do is find the number of vertices, how many number of vertices are there, then find the number of edges. So equal number of edges, equal number of vertices. Then we can go and check whether they are isomorphic or not based on the conditions. I came to know here V1, it has two edges. So I checked here V1, it has two edges. So when it goes two edges, here it is going to V2 and V3. So it has two connections. So within the bracket, whatever the corresponding vertex you should write as these two vertices. So I wrote V3, since V3 is already there, I wrote V3, other one I wrote V2. Again from this, whatever the edges is going, it should go to V1 and V4. So I checked, it's going to V1 of this graph itself, V1 and V4. Yes, it is going. Then from again V4 I checked, V4 is this, V3 and V2. Yes. And then again from V3 you check, it is V1 and V2. So you got to know what are the corresponding vertices. Now what will be the corresponding edges again? So whatever this edges itself, you list it out. Whatever this edges itself, you will list it out. So one-to-one correspondent edges, one-to-one correspondence edges are V1 to V2. V1 to V2 over here is what? V1 to V2. V1 is this, V2 is there, but here it is V1 to V4. So V1, V2 of your first graph is corresponding to edges of V1, V4 of your second graph. You see V1 and V2, whatever I written is first graph. So here it is V1 and V2. Come in this order itself. V2, V4. V2 is here, V4 is here. So it is V4, V2 of your first graph you write as it is. Whatever is this in bracket, right? Those are the vertices of your first graph. So V2, V4. V2, V4. So what is the corresponding edges it is? V4, V4, and v2, v4 and v2. Next you come over here, it is either it could be v1 v3 also, you can write v1 v3 v1 v3 v1 v3 or v3 v4. So v1 v3, you check what are the v1 is here, v3 is here, but here v1 is this, v3 is this. Here v1 and v3 of first of all, so it is v1 comma v3. Okay, one more edge is left, that is v3 and v4, v3 and v4. So v3 is here, v4 is here, so it is nothing but v3 and v2. So there is one-to-one corresponding edges as well as one-to-one corresponding vertices. Since there is one-to-one corresponding between the vertices and edges, therefore these two graphs are isomorphic. Therefore these two graphs are isomorphic. Okay, so thing is, first you have to find number of vertices between both, whether they are equal, and number of edges between both, and then you have to find one-to-one corresponding between the edges and the vertices. If there is a one-to-one correspondence between both the graphs, then these two graphs are isomorphism. So it's been proved that these two graphs are isomorphism. So let us go to the example 2. Prove that two graphs shown below are isomorphism, they have told. Prove that these two graphs shown below are isomorphism. So what we have over here is, we have A, B, C, D, and then again this is a different diagram, this is a different diagram, and then they you check for number of vertices again, how we checked over there. So totally 1, 2, 3, 4, 5, 6, 7, 8. So here also you have 1, 2, 3, 4, 5, 6, 7, 8. Check for the edges, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are 12 edges. Check over here. So 1, 2, 3. Okay, one we'll put it for outer. First we'll put it for outer. No confusion. That is 1, 2, 3, 4, 5, 6. We're done with 5, 6. Then we have 7, 8, 9, 10, 11, 12. So there are 12 edges and there are totally 8 vertices. So that is matching. So now we have to find one-to-one correspondence between both the graphs. Now we have to find one-to-one correspondence between both the graphs. So how we'll find the one-to-one correspondence? One is based on the vertices and other one is based on the edges. So one-to-one correspondence, if you're supposed to find, then you need to check for A. If you take this A, okay, A to B it is going, A to P it is going, and A to D it is going. Go over here, A, check. If I take that A itself, it should go to A to B. Yes, it is going. A to P. Yes, A to D. So I can put the correspondent for this is A itself, because okay. Now go with B. B to A it is going. Yeah, B to A it has to go. It's going to B to A. Okay. B to Q it has to go. Yes, it is going. And B to C it has to go. Yes, it is going. So I can take this as B. Similarly, go to C. From C you have C to B, C to D, and C to R. Check with this C. C to D, C to B, and C to R. So I can make this as C. Check with D. From D it is going to S, A, and C. A it is going, C it is going, S it is going. So yes, it is matching. So similarly, if you check with all the vertices A, B, C, D, then you have P, Q, R, S. So if you go with P, P to A, S and Q, P to A, S and Q. So I can make this as P, I can make this as Q. If you check for Q, it is R, B, and P. R, B, and P it is going. So this also would be corresponding to R, and this also will be corresponding to S. So same vertices whatever is there, but in other cases it may not be same. If it is A over here, it would map to something else over here. Okay, but in these 3 examples it is mapping to the similar objects, similar vertices. That's fine. So we got one-to-one correspondence, also one-to-one edges. So let us list out those one-to-one corresponding vertices. First you're going to write one-to-one correspondence, one-to-one correspondence between the vertices. Okay, one-to-one correspondence between the vertices. So just write what are the one-to-one correspondence vertices. A to A dash, A to A dash. So this is first graph, this is second graph. So A to A dash, B to B dash, C to C dash, D to D dash, put a comma over here, D to D dash, and P to P dash, P to P dash, and Q to Q dash, and R to R dash, A to A dash, B to B dash, C to C dash, D to D dash, P to P dash, Q to Q dash, R to R dash. Okay, R to R dash, and then you have S to S dash. A to A dash, B, C, D, P, Q, R, S to S dash. So these two things. So you came to know there is a one-to-one correspondent between these vertices. After that, once you got one-to-one correspondent between these vertices, you're going to find one-to-one correspondent between the edges. One-to-one correspondence between the edges. So if it is AB, what is the corresponding edge over here? There it would be, you know, all are matching. So if it is AB over here, it would be A dash, comma B dash. If it is AB is done, total 12 edges are there. If it is BC, then it would be B dash, C dash over there, B dash and C dash. If it is CD, CD, then there would be C dash and D dash. If it is AD again, then it would be A dash and D dash. So we are done with outer edges AB, BC, CD and AD. Now AP, we'll try with AP, that is internal edges. If it is AP, then we know that correspondent edge is A dash, B dash, because we have noted those, all these are having same vertices and same, I mean B is B dash K, so it would be same. AP means it is A dash, B dash, okay. And then you have BQ would be B dash and Q dash, and then you have CR, it would be C dash and R dash. Then you have DS would be D dash and S dash. Okay, D dash and S dash. So we are done with AP, BQ, CR and DS. Then we'll write PQ would be P dash and Q dash, and then you have QR would be Q dash and R dash. Then you have RS would be R dash and S dash. Then you have PS would be P dash and S dash. So if you see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 edges correspondence is done. 1-to-1 corresponding between the vertices is also followed, and 1-to-1 corresponding between the edges is also followed. Therefore, these both graphs are isomorphic. Therefore, these both graphs are isomorphic. Therefore, these both graphs are isomorphic. So this is regarding the example 2. Next, let us see the example 3. Show that the two graphs shown below are isomorphic. So the first one is U1, 1, 2, 3, 4, 5, 6. Check for, see whatever is written in the outer is not that. Whatever V1, V2, V3, they are written, that is the actual vertices. So see that 1, 2, 3, 4, 5, 6 vertices are there. Even here you have 6 vertices, and each vertex has 3 edges. Here if you check, it has 3 edges. So 3 means 1, 2, 3, 4, 5, 6, 7, 8, 9. So check with the 9 edges. 1, 2, 3, 4, 5, 6. Okay. And then you have this entire thing is 1 edge 7, and this entire thing is 1 edge 8, and this entire thing is 1 edge 9. So that there are equal number of vertices and there are equal number of vertices. Now we'll find 1-to-1 correspondence between the 1-to-1 correspondence between the vertices. 1-to-1 correspondence between the vertices. Okay, 1-to-1 correspondence between the vertices. So if you see, take u1 as this, it has to go to u4, u3, u5 and u6. So if you see, all this has 3 each vertices itself. All these has 3 each vertices itself. So I'll just color this. This was written already there in the text. We will not get confused with that. I'll put it as so this was already there in the textbook. That's why I just, not to create any confusion, that's why I'm just coloring that. Okay, someone has marked in the text. That's it. Okay, so u1, if you take u1 over here, and if you take u1 has 3 edges. If I take v1, for example, if I put u1 over here, if I take v1 over here, that means from u1 it has to go to u4, u5 and u6. So you can take anything. If I take u1 as this, it has to go to one edge is going here, one edge is going here, one edge is going here. So what I do is, here it is v6. So from u1 it is going to v6. So I can make this as u6. So this is u1, this is u6, and it is going to u4 and u5. So I'll make u4 as this itself and u5 as this. Okay, I'll just change the color. u5 as this, u6 as this, and u1 as this, and u4 as this. Now I got to know, left out is 2 vertices, that is, go to u2, u2 should connect to u4, anywhere, just go to, okay, you have u5 and u6. If u5 is there, it has to be connected to u1, u2 and u3. So u5 is there, it has to connect to u1 is there, u2 and u3. So what I'll do is, I'll try to connect this to, try with u2. If it is u2, then u2 has to connect to u4, yes, u2 has to connect to u4, and it has to connect to u5. u2 has to connect to u5 and u6. So u5, u6, you can take u2 over here, and then left out is u3. Okay, so no confusion, you have u3, u2, u5 and u1. So this is u1, u2, u3, and this would be u4. Okay, so we got the corresponding for this, for that means u1, u4, u3, u6, u2 and u5. Now 1-to-1 corresponding between the vertices, you can just write u1 is within the bracket is of your first graph. So directly write u1 is correspondence with v1, comma, u2 you find, u2 is correspondent with v5, v5 is of the second graph, u3 is correspondent with v4, next is u4 is correspondent with v2, next is u5 is correspondent to v3, next is u6 is correspondent to v6, u6 is corresponding to v6. So we got to know that these two graphs are having 1-to-1 correspondent between the vertices. Next we'll find the 1-to-1 correspondent between the edges. 1-to-1 correspondence between the edges. So if you want to find 1-to-1 correspondent between the edges, between the edges, so whatever is similar to that, you're going to write. So check for how many 9 edges we have to do. 9 edges we have to do, that is u1 to u6, u5, u4. So u1 to u4. So just write all those edges. I'll just change the color. u1. One is u1 and u4. I wrote here u1 and u4. One more is u2 and u5. That is u1 and u5. Other one is u1 and u6. Okay, so this is u1, u4, u1, u4, u1, u5, u1, u6. So whatever is u1, u4, check for u1, u4. u1 is here, u4 is here. So it is v1, v2. v1, v2. u1, u5. It is u1 is v1 itself. So v1. What is there for u5? u5 is v3. So v3. What is there for u1, u6? u1, u6 is this, so it is v1 v6. So this is one set of edges. Next you have u2 to u4 u5, u2 to u4, u2 to u5, u2 to u6. Okay, you have u2 to u4, u2 to u6, u2 to u4, u2 to u5, and u2 to u6. So u2 means what is there in this u2? u2 means v5. So just write v5, v5, v5. Check for what is u4. u4 is v2, so it is v4, v2. Check for u5. u5 is v3. Check for u6. u6 is v6. So this the 6 again, remaining 3 I'll just place it over here. So next it is u3 to u4, u5, u6. So u3 to u4, u3 to u5, and u3 to u6. So the corresponding edges for u3, check for u3 what is that? It is v4, and u4 is v2. So it is v4, v2, and then you have u3, u5. u3 is v4, u5 is v3, and u3, u6. u3, u6 means v4, and u6 means it is v6. So there is totally 1-to-1 corresponding between all the 6 vertices, and there is 1-to-1 corresponding between the 9 edges. Therefore, both the graphs are isomorphic. Both graphs are isomorphic. So this is regarding the example 3. Example 4, show that these two graphs shown below are isomorphic. So we have the two graphs over here, v1 as well as totally there are 10 vertices. So if you check here, even here you have 10 vertices, and then you have 1, 2, 3, 4, 5. So if you check over here, inner we have 1, 2, 3, 4, 1, 2, 3, 4, 5, and if you see in the star you have 1, 2, 3, 4. Okay, 1 and 2, 3 and 4, and then you have 5, 6, 7, 8, 9. So 9 plus how many? 5. So totally you had 5. Then you had 6, 7, 8, 9, 10. 10 you had. Then with this is one edge, this is one edge. Okay, and then you have this is one edge and this is one edge. So totally there are 14 edges. So check over here also. You had 5 over here. Check for this 1, 2, 3, 4, 5. Yes, 10 is done. Then you have 1, 2, and 3 and 4. Again it is repeating. So totally 14. Again 14 over here. So there are totally 10 vertices and there are 14 edges. Then you have to check whether they are 1-to-1 correspondence is there or not. So let us check the 1-to-1 correspondence are there. So if you check over here, v1 is connected to v6, v5 and v2. If you check over u1 is connected to u5, u6 and u2. So if you check here also, v1 is connected for v5, v6 and v2. So I can put for u1 as v1 itself. I can put for u1 as v1 itself. Go to u2. Where is u2? Sorry, v2. v2 is connected to v1, v3 and v7. So u2 is connected to u7, u1 and u3. So this can be v2. So whatever the outer pentagon is, we can make it as outer pentagon is inner. So we can make it as v3, v4 and v5 itself. Check for v5 in this v5. v5 is connected to v10, v1 and v4. v1 is u1, u4 and u10. u10 is nothing but v10 itself. Similarly, this would be v6, this would be v7. Check for this v7. v7 is connected to v2, v10 and v9. This is v2, v10 and v9. So you can put v9 and we can put v8. So when we put the vertices back over there, the number of edges is also equal and the number of vertices is also equal. So I'll be not writing again like how I've written over here. So just write same way how you have 1-to-1 correspondence between the vertices, as well as 1-to-1 correspondent between the vertices and 1-to-1 correspondent between the edges. So totally there were 10 vertices. You need to write the correspondence, and then you have totally 14 edges that you need to write to have the correspondence. Since both are one-to-one correspondence, both the graphs are isomorphic. Similarly, how we have written in the previous example, same way you need to write. I just showed how it is, how I'll do the mapping over here. So this is regarding the example 4. I'll not write the one-to-one corresponding between the vertices and edges because I already shown you v1 means u1, v2 means u2, v3. So just write all the one-to-one correspondence at vertices as well as the one-to-one correspondence edges, and then finally tell both the graphs are isomorphism. Okay, so this is regarding the example 4. In the example 5, you're supposed to prove that the two graphs shown below are not isomorphic. So if you want to show that they are isomorphic, there should be an one-to-one correspondence between the vertices as well as one-to-one corresponding between the edges. Now check over here, how many vertices are there? 1, 2, 3, 4. 1, 2, 3, 4. Yes, vertices are having some correspondence. I mean, there are one-to-one mapping we can do. But find the edges. We have 1, 2, 3, 4, 5 and 6. Check over here. 1, 2, 3, 4, 5, 6, and this is 7th edge. So here itself we came to know that there is one extra edge and there is no one-to-one correspondent between the edges. So these two graphs are not isomorphism. So what we can write the statement over here is, we observe that the first graph has four vertices and 6 edges, and the second graph has 4 vertices and 7 edges. As such, one-to-one correspondence between the edges is not possible. Hence, two graphs are not isomorphic. Okay, so this is regarding the example 5. Example 6, show that the two graphs shown below are not isomorphic. So they are told that these two graphs should not be isomorphic. So check for the number of vertices. You have 1, 2, 3, 4, 5, 6. Here also you have 1, 2, 3, 4, 5, 6. So vertices are having, there are equal number of vertices. Correspondingly, check for edges. You have 1, 2, 3, 4, 5, 6, 7, 8, 9. Check over here. 1, 2, 3, 4, 5, 6, 7. Sorry, 1, 2, 3, 4, 5, 6, 7, 8, 9. Edges are also corresponding. But how can we prove that those both two graphs are not isomorphic? How can we prove that both the graphs are not isomorphic? So we can show that these two graphs are not isomorphic by finding the number of edges of each vertex. Okay, by finding the number of edges of each vertex. So we'll go with a vertex which has 3 edges in this particular graph. So check for 1, 2, 3. So this is a vertex which yellow color marks means it has 3 edges. 1, 2, 3. Check for this, it has 4. Okay, any other graph that has 3 edges? Yes. So this is 3. So we can see over here it is 1, 2, 3. So 3 edges over here. And as well as check for the edges which has 2 edges. So this is the vertex which has 2 edges. So this is 2. Whereas 4 edges, we'll mark it in red. 1, 2, 3, 4 edges. So this is red. So 1, 2, 3, 4. So yellow means 3 edges. Blue means 2 edges, 2 edges. So here this is 3, this is 3, this is 4, this is 4. So there are 2 vertex of 2 edges, and there are 2 vertex of 4 edges, and there are 2 vertex of 3 edges. That is of the first graph. Similarly, find in this whichever the vertex has 2 edges, you mark it with the blue color. So go with blue, whichever has. So here you can see 1 2 1 2 1 2. So these three. So you can see here itself there are three vertex with two edges. So whether the two vertex with two edges, three vertex with two edges. So obviously there is no correspondence. Let us see again for the four edges. Four edges means it is red color. So it is 1 2 3 4. So this vertex is there. Again check for this 1 2 3 4. So this vertex is there. This vertex is there. So there are three vertex with again how many edges? Four edges. So here itself their correspondence is been lost because two vertex, two edges, they should be like same. If three vertex has two edges over here, similarly three vertex should have two edges over here. So there is no, in case if you have equal number of edges also, if you have equal number of vertices also, then graph you cannot predict until you find one-to-one corresponding between the vertices as well as one-to-one corresponding between the edges. You will not come to know whether it is isomorphic or not, even if you have equal number of edges and equal number of vertices. So this is an example of such type. So you can write down there. We note that each of two graphs has 6 vertices and 9 edges. Okay, but the first graph has 2 vertices of degree 4, whereas the second graph has 2 vertices of degree 4. You can see here, whereas the second graph has 3 vertices of degree 4. Therefore, there cannot be any one-to-one correspondence. There cannot be any one-to-one correspondence between the vertices and between the edges of two graphs and between the edges of two graphs. Hence the two graphs are not isomorphic. So this is regarding the example 6. Example 7, show that the two graphs shown below are not isomorphic. So check for the number of corresponding vertices over here. So you can see here 1 2 3 4 and outside 4, here also 4, inside 4. Check for the edges 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15. Okay, there are 15 edges. 1 2 3 4 5 6 7 8 9 10 11 12 13 14. Okay, wait, I missed somewhere or I repeated terms, I guess. So 1 minute. Check for the edges 1 2 3. I marked here 2 times, so it is actually 14. So here also 14, here also 14, and then again vertices are also in terms of equal. But check now, what we are supposed to do is check between the pair of vertices whether they have equal number of edges or not. So if we go with this, there is 1 2 3. Okay, go with this also, it is 1 2 3. So there are 2 vertices with 3. Here you go 1 2 3 4. So I marked it with red. Here you go 1 2 3 4. I marked it with red. Go to this particular point. It is 1 2 3 4. So I marked it with red. Go to this edge 1 2 3. Okay. Go to this 1 2 3 4. So I marked it with red. Go to this. It is 3. So I'll take blue color again back. Over here 1 2 3. Then over here 1 2 3. So you have exactly 4 vertex with 4 edges and 4 vertex with 3 edges. Okay, so for 3 edges we had marked with blue. Come back over here. So I marked with blue 3. Okay, this vertex is 3. This vertex is 3. Okay, there is 1, 2, here also 1, 2, 3, here also 1, 2, 3. Okay, here it is 1, 2, 3, 4, here it is 1, 2, 3, 4, here it is 1, 2, 3, 4, and here it is also 4. So the color we choose is red for the 4. Yes, here 4, here 4, here 4, and here also 4. Yes, we got the equal. But thing is, they've told that show that both the graphs are not isomorphic. Then what? Here even vertices are equal number, edges are equal number. There are 4 vertex with 4 edges, and here 4 vertex with 3 edges. But thing is, adjacency also should be maintained. If you remember, one-to-one correspondence between the vertices and adjacency of the vertices should be maintained. Adjacency of the vertices should be maintained. But in this case, we don't have adjacency of the vertices. If you see in the first graph, here the first graph has a pair of vertices. That means this vertex, pair of vertex. So this pair of vertex and this pair of vertex, which are not adjacent. That means it has the number of edges. Okay, it has the number of edges. That is, here you see this shape and this shape, but they are not adjacent. But here you check for this triangle shape and this triangle shape, which has adjacency of degree 4. That means here you check. This is a pair of vertex, degree 4, degree 4. If you check over here, degree 4, 1, 1, 2, 3, 4, and here also blue is with the degree 4, right? Wait, degree 4 we have within the red color. Yeah, 1, 2, 3, 4. Here there is pair of adjacency between these with the 3 degrees and 4 degrees. But if you check, there is no pair of 4 over here. If you check, there is no adjacent. Adjacent means what? Near to that. If you check for the degree, again 4, degree 4, here there is an adjacency. Here also for the 3 edges there is an adjacency. But in case if you check over here, there is no adjacency. So adjacency is present in the second graph, but is not present in the first graph. So based on this graph is not isomorphic. So can just write. We note that the first graph has a pair of vertices. Okay, pair of vertices. Why pair of vertices? Here see, these two pairs. This is a pair with 4 vertices, 4 degrees, and this is a pair with 3 degrees. Okay, pair of vertices of degree 4 are not adjacent. Whereas the second graph has a pair of vertices of degree 4 which are adjacent. Therefore, the two graphs are not isomorphic. So overall, from example 1 to example 7, if you have seen, how would you say that both the graphs are isomorphic? You check for the degrees of edges as well as the number of vertices as well as the edges. Now, when you came to know regarding not isomorphic, you checked with the number of vertices as well as the number of edges. So in these two graphs, when you compared, one edge was more, so immediately you came to know. But when you compare these two graphs, you had equal number of edges and equal number of vertices. But if you compare with the vertex wise, you got that edges were unequal. But when you came over here, you had edges also equal, vertices also equal, as well as when corresponding to each vertex also you had equal terms. That is, 4 vertex had 4 edges, 4 vertex had 3 edges. Here also you had. But only drawback is between the adjacency. That means in the second graph you had adjacency, in the first graph you did not have the adjacency. So based on the adjacency also isomorphic is different. So that's why it's told that these two graphs are not isomorphic. So this is regarding the example 7. So let us go to the example 8. Show that the two graphs need not be isomorphic even if they have same number of vertices, same number of edges, even if they have same number of vertices, same number of edges, and equal number of vertices with same degree, and equal number of vertices with same degree. So there are three constraints over here. Same number of vertices, you know what is the concept of same number of vertices, same number of edges, and equal number of vertices with the same degree, okay. So that is the question given. So we need to take two graphs, and then we are supposed to prove that whether those two graphs are not isomorphic. So let us take an example and prove it. Consider these two graphs. So we can see over here we have same number of vertices, that is 1 2 3 4 5 6. Here also 1 2 3 4 5 6. So we got same number of vertices. Check for the same number of edges. 1 2 3 4 5. 1 2 3 4 5. We got same number of edges and equal number of vertices with same edges. Equal number of vertices with same edges means check for V5. V5 has one edge, V6 has one edge. Check for V4. V4 has 3, that is 1 2 3, and V3 has 2, and V3 as well as V2 has 2, that is one this side, one this side, and one this side, and one this side, and V1 has 1. So just check. V5 has 1, V6 has 1, V4 has 3, V3 and V2 had 2, and V1 had 1. So there were so many edges over here. Check over here. You have A with 1, B with 2, and C with 3, and Q with 2, and then P with 1 and R with 1. So if you see over here, 1 2 3 with 1 edges, so 1 2 3, and 2 vertices with 2 edges and 1 vertex with the 3 edges. So show that the two graphs need not be isomorphic even if they have same number of vertices is satisfied, the same number of edges is being satisfied, and equal number of vertices with the same degree is being satisfied. So we draw such a graph. Even if we have such things, that is, we observe that both graph over here has 6 number of vertices and 5 edges. Further, in each of them there are 3 vertices of degree 1 we had seen, and there are 2 vertices of degree 2 and 1 vertex is of degree 3. And thus the two graphs have equal number of vertices with same degree, but the two graphs are not they are not isomorphic, because there are, if you see over here, there are two pendant vertex. There are two pendant vertex which is corresponding to V4. Pendant means pendant means which doesn't have only one particular vertex. Pendant vertex is nothing but which has only one edge for that. Okay, pendant vertex is always which has one edge for that. So there are two pendant vertex for this V4. Okay, come back over here, C. Okay, so if you see C over here, it has a B, but it is not a pendant vertex. It has two edges. If it has Q, it is not a pendant edge. Pendant vertex. Only P, that means here one pendant vertex, here two pendant vertex. So check over there. There are two pendant vertex adjacent to the vertex V4, that is V5 and V6, whereas one pendant vertex in the C. Okay, in the second. As such, the adjacency of vertex cannot be preserved. Why? When you do the adjacency also, the edge corresponding also should be the same. Adjacency is not being preserved in the second graph. So therefore, since there is no one-to-one correspondence between the vertices, then the graph is not an isomorphic. So you can just write, we observe that both the graphs have 6 number of vertices. So you can write over here. We observe, I'll write in a new page. We observe that both graphs have the same six vertices and 5 edges. Further, in each of them, there are 3 vertices of degree 3 of degree 1, sorry, namely V1, V5, V6 in first graph, and A, P, R in the second graph. There are two vertices with degree 2, that is namely V2, V3 in first graph and B, Q in the second graph. And there is one vertex of degree 3, there is one vertex of degree 3, that is V4 in first graph and C in the second graph. Thus, the two graphs have equal number of vertices. Thus, the two graphs have equal number of vertices, but the two graphs are not isomorphic. Because there are two pendant vertices adjacent to vertex V4, adjacent to V4 in the first graph, but there is only one pendant vertex, adjacent to the vertex C in second graph. So this is regarding the example 8. So we proved that all the satisfied condition we matched and we draw a diagram, but we proved that that is not isomorphic just by these two pendant vertex V5 and V6 as well as with the P. Since V4 had 3 edges, in the 2 are pendant vertex, here C had 3 edges, 1 is pendant vertex. So there is no one-to-one correspondence between the vertices of the graph. That's why it has been proved that those two graphs are not isomorphic. So let us go to the example 9. Show that the following diagrams are isomorphic. So if we just see over here, it is a directed graph. So it is a directed graph. So you need to find the correspondent. Till now we do not have the directed graph. So we need to find the corresponding vertices as well as the edges again. So consider over here you have 4 vertices as well as 4 edges. So we can check for the process. So if it is A, what is the corresponding edge you are supposed to find? So just check over here. A has 2 edges, A to B. So if I take this as A, then this has to be, if I take this as A, I just put on here. Okay, if I just take this as A, it has one outgoing edge and one incoming edge. So if I put P over here, for P if I put A, okay, so one outgoing edge is corresponding to again what? B, and incoming edge to A is corresponding to be D. Okay, and then left check for D itself. One outgoing edge should go to A. It is going to A, and one incoming edge should go to C. So this will be C. So this is how you are going to find the vertices and the correspondent edges. So you should write 1 to 1 correspondent vertices, 1 to 1 correspondent vertices are A to this, what is that? A to P, B to S, and C to R, and D to Q. So this is 1 to 1 correspondence, and there is 1 to 1 correspondent between the edges also. So write down the 1 to 1 correspondent edges. So it would be A to B means it is P to S. So A comma B is P comma S, and B to C is B and C is there, it is S to R. So B comma C is S comma R, and then you have C to D. C comma D is nothing but R to Q, and then you have A to D to A. Sorry, A to B, B to C, C to D, D to A. Directed edge it is A, D to A. So D to A means it is Q to P. So there is a 1 to 1 correspondent between edges and the vertices. Therefore the graphs are isomorphic. So these are the different example of isomorphic problems. All 9 problems are different from each other. So kindly learn it clearly and understand the concept of isomorphic. So if you want to find it to be an isomorphic, you should find the number of vertices, number of edges. Even if you have a number of vertices and number of edges, again within the graph each vertex might have the degree different. Even if the degree is equal, but adjacency may not be the same, or like we have seen in the previous example, like pending vertex was different and there was no adjacency. So these all constraints you are supposed to check, then only the graphs are said to be isomorphic. So this is regarding the isomorphic problems.